All right, so this is part 3. And so before we get to drowning swimmers, we were just talking quickly about L'Hopital's rule and calculating what is the limit as x goes to 0 of sine of x over x. If you use L'Hopital, you would get its cosine of x over 1, which is 1. But really, this is cheating, because if you're going to say the derivative of sine of x is cosine of x, you need to already know the limit as h goes to 0 of sine of 0 plus h minus sine of 0 over h is 1. So by knowing that this limit is 1, you can then calculate that this limit is 1 in a longer way. So you can use L'Hopital's rule, but you can't use L'Hopital's rule unless you've already shown that the limit you want to calculate is equal to 1. Okay, so before we go on to more things, since most people don't seem to be aware of the drowning swimmer problem, let's talk about the drowning swimmer. There's a lot of good variants. There's some beautiful articles, Do Dogs Know Calculus? And they're really, really fun. I'm sorry?
I've seen one where they have like a dog like jumps in the water.
Yes. I think it's Tim Pennings, and his dog is named Elvis. Yeah. So I've actually met both of them. So here, forgive my artistic creation, is our lifeguard. And here is the drowning swimmer. Okay? And the swimmer is in the water. So in all these problems, the very first thing you should ask is, what is your goal? What are you trying to do? Get to the swim in the least amount of time. We will assume for convenience that there is no one else on the beach, and that all paths, the lifeguard runs on land at a certain rate, and the lifeguard swims in the water at a certain rate. Without loss of generality, you can choose either the land speed or the water speed to be 1. And that's just the units you're using. With a little bit of thought, you can quickly realize that there's really only one type of path the lifeguard can choose. The lifeguard runs at some angle to the shoreline and then moves directly to the swimmer. Any other path will clearly be worse. If I do any kind of spiraling path, that's more time. If I run backwards, that's stupid. If I run over here, that's stupid. So I pick some point, maybe it's here, and I run straight to here, and I go at an angle like this. If you teach a certain science, you've actually seen this problem. So this occurs in physics. Yeah, change in media. So if what path does light take when it goes from one media to another? It bends. And in fact, light takes the path of minimal time. So most people would say, just run straight to the swimmer. If any of you are training future lifeguards, I strongly urge you to just tell the person, just run straight for the swimmer. The savings is negligible. Worst thing to be would be the swimmer is drowning and the lifeguard takes out a piece of paper and starts trying to calculate the optimal path. So you always want to choose good units. What should this location be? 0. What should this location directly under the swimmer be? 1. And that's all the freedom we have for distances. So now we have some distance up, and we have some distance down. Right? We no longer have any freedom on that. So if you want, we can make this A, we can make that B. We'll have this location here as x. And then we have a land speed and we have a water speed. Where do you want the speed to be 1? Land or water? Or does it matter? Doesn't matter. So which do you want? Land. Okay. So V land equals 1, and then we have V water. So we want to calculate the time. And the time is going to be distance divided by speed. So time will equal time on land plus time in water. So the time is actually going to just be a function of x. Right? The 3 natural points for x are run straight to the water, run straight below, or go just diagonally straight for the person. without loss of generality, we can eliminate one of these paths as being really bad. Which do you think is the worst possible path you could take? Yes, straight to the water. You're minimizing your time on land and maximizing your time in the water. So almost surely this will be bad. Unless you're a penguin. And so you might be a person where somehow you actually swim better. My daughter loves penguins. We have a giant stuffed penguin we got from the Williams Mystic Aquarium. So if you happen to have a penguin lifeguard, this would be a candidate.
Or it's extremely soft sand.
Or extremely soft sand, where you're running on sand. We would expect the water to be less than the land. It doesn't have to be, but we would expect that to be the case. It's nice whenever possible when you're doing these problems to have some kind of physical intuition. And so in most situations, we expect the candidate will either be running over here to maximize time on land or maybe move back a little bit. All right, so let's calculate. We need to figure out what is this length here. So how would I calculate this length? Pythagorean theorem. So this length would be a squared plus x squared, square root. And the length over here would be 1 minus x squared plus b squared. And then remember, VW, this is given to us. This is known. So anything in blue is known. So maybe I'll make x red. So the blue values are known. It's the x that we want to figure out. And so we get the total time as a function of x is going to be the square root of a squared plus x squared over 1. Distance divided by distance per time will be time, plus the square root of 1 minus x squared plus b squared over VW. So how do we find the best value of x? So we want to find the minimum. So how do we find the minimum of this? So we find where the derivative is 0, and then we also have to check the endpoints. So the two endpoints are going to be x equals 0 and x equals 1. And so now we get t prime of x. Now we get the fun of taking the derivative of this. So you'll get 1/2 a squared plus x squared to the negative 1/2. And then the derivative of the inside will be 2x. Plus, now we'll have 1/2 1 minus x squared plus b squared to the negative 1/2. Now we take the derivative of the inside here, so we'll get 2 negative 2 1 minus x over VW. And that should equal 0 for our candidate point. All right, so now let's see. The 1/2 cancels with the 2. The 1/2 cancels with the 2. The negative, we'll put that over to the other side. We'll get x over a squared plus x squared to the 1/2 is 1 minus x over VW, and then 1 minus x squared plus b squared to the 1/2. What should we do? Square both sides, and after we square both sides, cross multiply. So if we square both sides and cross multiply, we'll get x squared VW squared 1 minus x squared plus b squared equals 1 minus x squared a squared plus x squared. So after some algebra, we'll get alpha 1, we'll say alpha 4 x to the 4th plus alpha 3 x cubed plus alpha 2 x squared plus alpha 1 x plus alpha 0 equals 0. It's going to be a cubic. And it's going to be a real honest-to-goodness cubic because the x to the fourth term here is negative x to the fourth. And over here it's going to be, we'll have a negative x squared, we'll have an x squared here, x squared here, but we have a VW squared which is less than 1. Oh, no, this would be a positive x to the fourth. The cubic term here is going to be a positive x to the fourth. Not the cubic, the quartic. The quartic term here, this side is going to look like x to the fourth plus blah. And on this side, it's going to look like VW squared x to the fourth plus blah. And because you don't travel the same speed on water as you do on land, they will not, it's going to be a real honest-to-goodness quartic. The alpha 4 is not going to be 0. In the special case, when your speed on water is the same as your speed on land, it should reduce to just the straight line. Okay? So we have now reduced it to finding the roots of a quartic. Well, fortunately, we talked about fixed points earlier today. We've talked about Newton's method last time. There are ways to find roots of polynomials like this. But in the break between sections, there was a comment that students are sometimes surprised when the answer is not a nice integer. What I like about this problem is you start off with something very simple. Someone is drowning. What's the best path to take? And all of a sudden, very naturally, a quartic equation comes up. How many roots should the quartic have? 4. So do you think that there are 4 paths that will be equally good? So it'll give us 4 candidates. Do we think all the candidates will be equally good? What's going on? Well, whenever you square things, you have the ability of introducing a phantom root. If you want to solve x equals 1, can anybody give me all the roots to x equals 1? All values of x such that x equals 1. What values satisfy this? 1. Right? There's a certain finger you could have held up because the problem is a little trivial. Right? If I square both sides, how many solutions do we have to x squared equals 1? 2. We have 1 and negative 1. They both don't satisfy this initial equation. We've introduced a phantom or an extra root. You sometimes see this in maximization problems where you could get a negative length is also one of the critical values. And students hopefully realize that you should not have a negative length for one of your dimensions. So over here, you will have 4 candidate x's. They might not all be real numbers. Some of them could actually be imaginary numbers or complex numbers. But you'll have 4 candidates. One of them will work. And then you just compare those candidates to the 2 ends. So I really like this problem because you start off, as I said, with a very reasonable problem. And then all of a sudden, you now see I have to find the solution of a quartic. I'm assuming everybody knows the quadratic formula, negative b plus. There is a formula for the solution of the roots of a cubic. There is a formula for the solution of the roots of a quartic in terms of the coefficients. There is not a formula for general quintic degree 5 or higher. It turns out there's a deep math theorem that once you get to degree 5 and higher, you can no longer write down the answer always in closed form in terms of the parameters. For degree 4 and lower, you can. And the story I've heard, I'm not sure if it's necessarily true, but it's one of the stories you like to believe, is that in the old days you could challenge someone for their mathematical position. And a couple of hundred years ago, the person who discovered the formula for the roots of the cubic, he kept that in strategic reserve. Because the only way you lose is if you can't do their challenge problem, but they can do yours. So no matter what challenge problem someone gave him, he would just give back, find the roots of these 10 cubics. And if you don't know the cubic formula, it's almost impossible to find these roots. Almost surely the story is not true, but it's a fun story, and I've deliberately tried not to investigate because I like to be able to tell it. Did I tell you the one about the stealth bomber, stealth fighter? So the other one, again, I'm deliberately not trying to investigate. I doubt the engineers were this careless. Is they're trying to maximize stealthiness. They're trying to make the plane that will be the hardest to see on enemy radar. And they looked for critical points. And they didn't check to see if they were at a maximum or minimum. So they built the I'm here plane. Again, almost surely not true, but if you're trying to talk to students and excite them or get them to remember the importance of something, yeah, we should have thought that, the big, gong was, a dead giveaway that something was, suboptimal. So you can then talk to the students, how would you solve a quartic? There is a formula, but how would you numerically approximate? You could also plot this. And you see as a function of x, what is the optimal value? So they've done some experiments with, a dog, and will the dog take the right path? It turns out that you can view this almost algebraically. And so I think you can bypass calculus in solving this. So there's a tweak of the problem, which is a little bit more interesting. So is everybody comfortable with this part? Yes. Very good. All right, so let's move on to the tweak. And if done properly, it actually allows us to prove one of the most important inequalities in mathematics. I'll see if I can actually remember how to do that. So here is, the very poorly drawn dog. Imagine you throw a bone to the dog. Okay? Because my artwork sucks, we will idealize it now to the dog is this point here, and I throw the bone here. What path will the dog take to the bone? Straight line. Right? Really not that challenging. What if I throw the bone over here? What path will the dog take? Straight line. What if I throw the bone over here? Straight line. Right? This doesn't seem that challenging. What if I throw the bone over here? Not necessarily. This dog knows calculus. Why might the dog not take a straight line to that point? I'm sorry? So this is a hypothesized, idealized situation. Nothing else is in the water. No. The bone will be fixed. We'll have it attached with an anchor and a very tight string so it can't move. What other path could the dog take? Yeah, the dog might go to land. So the dog goes at some angle to the land, runs on land, and then comes back. They actually do that. So they actually did the experiment, and the dog was doing a pretty good job of figuring out what angle to run to land, how long to run up, and then how to run back. So the idea is, for a lot of things in life, at every moment in time, do what's locally best. If you give this advice to your students, how much time will they spend studying? None, because locally what's best for me right now is let me party with my friends or watch TV or play video games. Future Steve can worry about studying. And future Steve never gets a chance to study. So at some point you have to bite the bullet and do work. If I want to get from this point to this point, locally, if I could only move for 1 second in time, what path will narrow the distance the most? What path should I take? Straight line. And so if at every moment in time you do what's locally best, it leads you to this path. So if you have to do what's locally best every single moment, this is the path you take. If, however, you can do what is globally best, then it might make sense to occasionally do something that's locally suboptimal. And that's where the longer path like this comes into play. So it becomes, of course, interesting to figure out where you should run. So there are extreme cases you can do. I'll see if I can do this well enough to actually get the really nice fundamental result. Let's imagine your speed in the water is 1 unit. And let's imagine your speed on land is plus infinity. This is a little bit unreasonable. What path should the dog take in this ridiculous extreme? So you can run at an infinite speed on land, and you swim at 1 unit per second on the water. Straight down. And in fact, I could even move this up a little bit. And so the path you would take is you go straight down, run straight underneath, and come straight up. So what's going to happen is there's going to be a bifurcation. So when you look at the path the dog takes, let's say this is going to be x units, this is going to be y units. And then, I have some distance over here. If y is if the second point is very close to the first, you just do the straight line. Even though you can run at plus infinity down below, the cost of going all the way down and then all the way up is such that it's not worth it. At what point does it become worth it to consider? So when this distance here is x plus y. So once this distance hits x plus y, it's worth considering going down, because you're actually indifferent at that point. And then as soon as this distance becomes greater, then you would actually rather go down and up. And there's a way to get from this, the inequality. Let's see, what is it? XY. So this is called the arithmetic mean. And this is called the geometric mean. So there's lots of different ways you can average numbers. The simplest one we most often use is just, add the two values and divide by 2. I'm assuming everything here is positive. Another thing you could do is you could multiply the two numbers and take their square root. Notice in both cases, if x equals y, both of these return the value of x. Good. If I'm averaging the same number, I should get back the same result. There are things you can do where if you have more than two numbers, what would you do? And you could actually say, I could add n numbers and divide by n versus taking the nth root of their product. There's actually a whole infinite family of things you can do in here. These are the two extreme cases. It turns out the arithmetic mean is always greater than or equal to the geometric mean. And the simplest proof is the square root of x minus the square root of y squared is greater than or equal to 0. This is one of the most important inequalities in mathematics. If you take a number and square it, it's non-negative. Well, if I expand this out, I get x minus 2 square root of xy plus y is greater than or equal to 0. So we get x plus y is greater than or equal to 2 square roots of xy, or x plus y over 2 is greater than or equal to the square root of xy. In fact, that's what I was doing quickly in my head to make sure I put the inequality in the right way. There's a faster way, though, and so this is just a really good way. Imagine you remember the functional form of an inequality, but you don't exactly remember which way things go. I remember there's some comparison. So I'm going to erase this now. And this is really good advice to students who can remember most of a formula but forget that little bit at the end. So I know there's some relation between x plus y over 2 and the square root of xy, but I can't remember which way things go. What should I do? Plug in values. So really good values to put in here is, let's take x equals 1 and let's take y equals 9. You could take 0 as well, and that would be OK here. If I take that, I'll now get the square root of 9, which is 3. And on this side, I'll get 10 over 2, which is 5. And so that tells me, in this case, it goes that way. So if I remember that there's a relationship like this, but I forget which way the inequality goes, I can actually correct myself by putting in one special value. And so there is a way, and I'll send you a link to the paper, to go from the drowning swimmer problem and actually get the arithmetic mean, geometric mean from imagining a dog running where you have an infinite speed on land. But what's fascinating is this idea of a bifurcation, that if the second point is sufficiently close to the first, the path you take will be a straight line. And as you get further and further and further away, it's still a straight line. And then you reach one point where you're indifferent. And then once you get beyond that point, you will now go to land. And so all of a sudden you will have a massive fundamental shift in the quality of the best fit line. Okay, so this is one of my favorite calculus problems. You missed the drowning. Did we do the Farmer-Brown problem with the areas and pens? But did we do them here? Okay. Okay. Let me do Farmer. Anybody read Click Clack Moo?
Yes.
Okay. It begins. Farmer Brown has a problem. His cows like to type all day long. They go click clack moo. I remember. I think the first time I was teaching calculus at Williams, I actually brought in click clack moo from one of my kids, and actually, read a little bit of the book. It's a fun story. So we'll do Farmer Brown, and then we'll do Farmer Bob. So Farmer Brown loves a certain shape. Farmer Brown will not consider any pens that are not what shape? Farmer, a little bit more general than square. Rectangles. Must be a rectangle. So maximum rectangle for a given perimeter. So you have x, so that should probably be y. So you have y, x. You're given, say, x plus y equals 40. You want to maximize x times y. So one way you can do this is you can say, well, I can solve, and this gives me y is 40 minus x. So then this becomes, my area is just going to be x times 40 minus x, or 40x minus x squared. So if I graph it, 0, 40, 20. And I'll get that the maximum is when I have a square. You could also use calculus at this point. It's actually better to first multiply things out so you don't have to use the product rule. So you can actually use just standard. And so if you want to use calculus, you get, a prime of x is 40x minus 2x. So the critical point is, just 40, thank you, is just 40. So you get the critical point is x equals 20, and then you note a of 0 equals a of 20. Wait a minute. I'm saying this is the semi-perimeter. I'm saying the semi-perimeter is 40, not the perimeter. Right? The whole perimeter would be 80. I'm saying x plus y is 40, not 2x plus 2y equals 40. So I'm saying the semi-perimeter is 40. So if I just check the extreme cases, they have no area. And so I get the maximum is when x equals 20. Okay, so here's the twist for Farmer Bob. So Farmer Bob is a lot like Farmer Brown, except he happens to be right on a lake. How many of you have seen the Farmer Bob problem? Okay, and so now, because they have the same parents, he also grew up in a house that only likes rectangles. But now, I would have x plus 2y equals 80. Before I had my perimeter was 80, so my semi-perimeter was 40. Now, Bob does not need fence on the bottom. So how would we find the best pen for Bob? Same process. Okay, so what would you get? The area, which is really x times y, how would I write that? All right, so one thing to say is it's probably easier to work in terms of y than x, right? Because I can solve, y is equal to 80 minus x over 2. Or I can say x is equal to 80 minus 2y. So I'd probably rather just do things in terms of y and get, a of y is going to be 80 minus 2y times y, which is 80y minus 2y squared. Right? So we get a prime of y is 80 minus 4y. So the critical point is going to be y equals 20. Is this right? Yeah, that's right. And then what will x be? Okay. I claim that there's a way to do this problem without calculus.
Well, you can write it as quadratic.
So you could write it as a quadratic. So you need to know your superheroes. So in the Justice League, who is the superhero who lives underwater? Aquaman. Right? I've always been a little bit confused about some of his powers. He can talk to fish. He can also somehow cluster water together and throw water balls and attack people with that. So let's get rid of the calculus, because a lot of it is, can you look at the problem the right way? Imagine at the same time Farmer Bob is trying to make his pen, you have Aquaman trying to make a pen for his fish. Do you agree that whatever Farmer Bob does for his cows up above, the mirror image will be optimal for Aquaman? Yes, it drops off immediately. Yes. The Legion of Doom somehow fired their lasers and just burned a trench. Yes. But you want to get the kids involved. So they mirror image each other. So this is the same as now the Farmer Brown with a perimeter of what?
2y, 2x.
What's the perimeter? Well, don't give me in terms of x's and y's. What's the 160? Right? We knew the initial perimeter was 80. Aquaman's perimeter is 80. So we have a perimeter of 160. So what's the answer? 40 by 40. So this is 40, this is 40, this whole thing is 40, so it's got to be 20 and 20.
It's kind of like looking at it when we did the triangle one earlier, when there was two of all the other pieces, we just think of something else to add in.
Right.
Easier.
Yes.
Doing partial integrals or integration by parts.
Right. And this goes back to the geometry proofs that the students love, where you draw an auxiliary line in a very clever way. And if you see the right way to draw the line, the problem becomes trivial. And if you don't, you just keep hitting your head. And so here, if you just imagine doing the mirror image simultaneously, you've reduced it to a previous problem that you've already done. And so you don't have to go through the analysis again.
So I taught that a bunch of times in Algebra 2 class with
Right.
quadratics. And, and then we do all that all the time. And the kids are like, oh, it's a square, and you give them the river problem. And they're like, it's a square, and they're like, it's not, you should have done the problem.
Right.
But I would have loved to see the kid do this and be like, see?
Right.
What?
It is a square. It's just half the square is submerged.
Yeah. That would have been cool.
And so then the question becomes, what if you do other shapes? So imagine you only can do a triangle and you have to do a side along. I have not thought of this. So you have to do a triangle, and one of the sides you get for free is the riverbed. So let's do it right now. We've got a couple minutes before pizza, right?
So she told me to plan on about 20 past 12.
Oh, 20 past 12.
So do you have enough materials?
Oh. Yes, but if I'm doing 35 minutes, that's different than if I'm doing 15 minutes.
Yeah, so she said to be on the safe side, 20 past.
Okay.
She just doesn't call it. She's been down there.
Not to live in the
Ah.
But she said she had to stand outside for about 45 minutes last time, so she gave up on that.
Right.
I don't mind that this part is being recorded. I was flying back on American Airlines. They changed my itinerary 7 or 9 times, including having me fly from DC to DC. I at least had a non-stop direct flight from DC to DC. That was good.
I mean, there was a flight that was supposed to go from LA to Tokyo. I ended up doing LA to LA in like 4.5 hours.
Wow. Was this the flight where somebody got on who didn't have documentation? They didn't have their passport.
No, they were on the correct flight. They just two siblings both had tickets. One had a ticket on X airline, one had a ticket on Y airline. They ended up going to the same.
Oh.
So he had a ticket to the same city.
Right.
Just on a different flight.
Oh.
Wait, so they wouldn't go there?
So they realized halfway through that there was someone on the flight who was not supposed to be there. So they
Turned the flight back.
Flew back to LA.
Right.
Took that person off the plane, and then the next day flew to Tokyo.
Wow.
And I really hope, I know this is being recorded, that they mention to all the passengers which person it was that is causing you to fly back to LA. So imagine.
I found out later that the other person who they had to get off the flight had a ticket, a valid ticket to LA, just a slightly different airline with the same price. So it's easier.
So here's my tweak now. I have not thought of this before. Let's say you have to do triangles, and you have one side fixed. And you have a given perimeter. So your perimeter is, again, 80. What shape do you think is going to be best? Equal. So one guess is an equilateral triangle. Another guess is a right triangle. Oh, okay.
Right.
But this is good.
Well, yeah, that's what I said to Larry.
So,
well, without the side length, it's an equilateral, and then.
But here.
Done it with the side.
But see, now you don't have to pay for this side. This side is now free. This is your water boundary. So if you don't have the water boundary, I agree that the equilateral triangle maximizes area. But now I'm giving you I'm just in a generous mood. I'm giving.
So it is a right triangle. Yes. Because you just do it down the middle.
So what you now have is you have something like this, right? And we have to choose where do we want to put here, and we'll have our x and we'll have our y, and x plus y equals 80. What does Aquaman do underneath? Same thing. So how should I do it? Should I do it like this? X and y. Or is there a better way to do it? Do it y and x. And so now if I do it like this, that's now y, that's now x. So if we do it like this, it's now a rectangle.
And the rectangle's half a square.
Rectangle's half a square. So now this reduces to Farmer Brown. Yes. And so it must again be 40 by 40. So what we're doing is we're doing sort of like a reflected mirror image down below. So Farmer Bob does something up top, or maybe we can't do Farmer Bob because Farmer Bob likes rectangles. We need another name beginning with B.
Bridget.
Okay, Bridget? Good. I was actually thinking Barbara, but you can do Bridget. There was a period of time when my son would only listen to the song Barbara Ann. It was a huge success when we finally got it to the point where he was willing to allow my wife and I to choose other songs on that album. So we have Farmer Bridget, who loves triangles and will only consider triangular pens and does not have to pay for the side down below. So when you give this to students, the two natural shapes are an isosceles right triangle or an equilateral triangle. And the fact that the side is free down here might mean that the equilateral triangle is not best. So she chooses something. And then Aqua Woman down below will do something similar. And instead of going X Y and making a parallelogram, it's actually better to do Y and then X. So it's a rectangle. It's just a rectangle where the water is now cutting along.
But how do you know it's a
diagonal.
rectangle?
I'm sorry?
How do you know it's a rectangle?
Because I go, if I put the triangle like this is going to be a right angle here, and this will be a right angle here.
You get to choose it.
But that's only if the first one's a right.
Oh, okay. Good point. So
Yeah, right. If you did the isosceles one.
you're right. Oh, good. So we might have to do more work on this. So if it's not a right angle, are we in trouble?
We
So
have
you
a
can still
parallelogram.
you can still
We would have
double
a
it.
parallelogram.
You can still double it to find it, but that's a different shape.
Okay. So now, so we might have a parallelogram. So I claim, so can we make the claim that if we have a parallelogram, that a rectangle would do better? So how would we make that claim? So you're absolutely right, we have to do a reduction first. I'm not sure if this is actually still getting in
The
the
area is always shorter than the height is always shorter than the side, right?
Yeah.
So let's see. Oh no, maybe the way you do it is we come down like this. So if we slice this over here and move this over here, we don't change the area. We don't change the bases. The area of a parallelogram is just base times height. So the area of this is the same as the area of this. But the perimeter here is larger.
Because it's Pythagorean.
Exactly. So what we can do is we could pass from this parallelogram to this rectangle. The area is unchanged, but the perimeter has gone down. And since the perimeter has gone down, we could then magnify it a little bit and get a larger area. So we know that if we don't have a right angle here, it can't be optimal. So you're absolutely correct. We have to do that stuff initially and say that if it is not a right angle there, it's not optimal. So we know there has to be a right angle here. Now that we know that, then we just reflect downward like that.
The light's red.
Oh, that's red.
Oh, you were right.
Is it supposed to be red?
Nope.
Green before.
Okay, we were just discussing that with the picture.
So, oh no, this was not.
Start again.
Yeah. So,
There we go.
all right. So I'm not sure how much of this was recorded,
Now
unfortunately.
you're red again.
I'm red again.
It was recording for a moment.
Okay,
It's
so-
red.
All right. This is a good place to stop.